And this right triangle has a perpendicular component, we call that FG perpendicular, and a parallel component, we'll draw it over here, because I like drawing from the center, that's the FG parallel, and we can find those out. Now, you can memorize them, or you can think of, there's that theta from before, the adjacent is the cosine, so FG perp is FG cosine theta, and we just did that up there, that came out to 8.7, and FG parallel is, that's the opposite, FG sine theta. And so that's 10 sine 30, and that comes out to 5 newtons. So this is 5 newtons, this is 8.7 newtons, and from this you could have then connected and say, oh, the FG perp, hash out our FG, we're not using that anymore. The perpendicular component balances the normal, that's why they're both 8.7. The parallel component for this picture, does it balance the FF? Don't assume yes, we don't actually know yet, but we're about to know. Constant speed. Constant speed, F net 0. Now we know everything balances, and because everything balances, the frictional force is also 5 newtons. Now that you've done this one, you actually could go back to that first example, example 13, and say, wait a minute, if the block is at rest, net force 0, the frictional force had to balance the FG sine theta because it was the full picture. This direction, parallel direction balances, perpendicular direction balances. All right, we're almost there. Example 15. Sliding down a frictionless ramp, 20 kilograms. You know FG is straight down. Don't play around with those angles. FG is straight down. 20 kilograms times 9.81 is 196. Let's just call it 200 newtons. Keep it easy. FG is 200 newtons. We know there's a normal force. We know that normal force is not 200 newtons, most likely. It's not 200 newtons. It's not terribly perpendicular, but your paper may look like that. Fn. And what else is going on here? Frictionless, so there's no friction, don't draw it. There's no talk of a pull, there's no springs. That's the whole picture. That's actually it. So you want to come up with the F net, as usual. We need the F net up here. So you got two choices. Make the resultant of these two, which is, for most of you, probably a bit of a mess. You may not be into that. Or break this into its components. And that's going to be the standard method I teach you. This FG is pointing both into the ramp and down the ramp. So it has an FG perpendicular component. Let's write that over here. And it has an, I'll draw it over here, FG parallel component. We know FG perp is FG 200 cos 45, and FG parallel is 200 sine 45. Conveniently, cosine and sine of 45 are the same. These come out to about 140 newtons. And so, 140, 140, and though the 200 is there, we don't need to worry about it. Let's hash it out so it doesn't distract our picture. It doesn't distract our thinking about the picture. Now, what is the net force? In the perpendicular direction, there is balance, which means the normal is 140. In the parallel direction, there is not balance. There is only FG parallel. And FG parallel is 140, and so that's the net force. Of course, you could find the acceleration, 140 over the mass is 20, which comes out to 7 meters per second squared down the ramp. F net is down the ramp. This is also parallel down the ramp. Good. Last one. Pulled up the rough ramp at a constant speed. Now this one, I'm not even worried about you solving it with actual magnitudes or numbers. This one, we don't even have quite enough info. We're just going to set up the diagram because that's the key. Pulled up the rough ramp at a constant speed. That's this pull force. Here it is. F external, 50 newtons. Good. What else do we have here? We know that there's weight. Even if we don't know what the weight is, we can draw a weight. We know that there's normal force. Even if we don't know what the normal force is, we can draw a normal force. Now, it's a rough ramp, which means friction. So we know there's friction. We don't know what it is. We can still draw friction. Now, this picture, hopefully, looks to you a bit incongruous. It looks like one of the forces does not quite align the way the others are, and it should. The one that doesn't align, FG. So let's align it. FG points both into the ramp and down the ramp. This is what we call the perpendicular component. And this, which I'll draw over here, is what we call the parallel component. So, hash out the FG. Even without numbers, we can come up with some useful information here. This says constant speed, straight up the ramp, F net is 0 newtons. Now, if F net is 0, we know something. We know we have balance. We have balance both in the perpendicular direction and the parallel direction. In the perpendicular direction, the normal force is equal to Fg perp. Cool. In the parallel direction, it's a little more complicated. The external force, which is pulling up the ramp, is balancing not just Fg parallel, not just friction, but both. And so, you actually have the combination of the two. F external is balancing both the parallel component of the weight and the friction. And this is a good equation to realize. In fact, of all the questions I've seen on the readings exam involving ramps, this is probably the highest rated as far as toughness. Not that bad if you have a nice picture and you say, oh look, these two are balancing this one. Alright, there's your free body diagrams, and I'll make an advanced scenario one for those who are interested. Peace.